Yeah. I just hit the button, the recorded button. Yeah, they're up. Yeah, I can do that. I usually leave it blank at the beginning to not, I don't want to give anything away. Yeah. But I think now's about the time, right?
All right. All right. Welcome, everyone. Thank you so much for joining today's version of the Grasp on Robotics seminar series. My name is Michael Poza. I'll be the faculty host for today. Quick reminder, you can go on YouTube and check out all the old talks. If you're on Zoom right now, use the Q&A feature there to ask questions, and we'll have some people watching that throughout the talk. Okay. We also have two students, Hyun Bui and Will Yang, who are going to be running our Q&A today, PhD students in Grasp. It's my pleasure now to welcome Zac Manchester. Zac is an assistant professor at the CMU Robotics Institute. Just a quick sort of brief bio on Zac. He did his PhD in undergrad at Cornell, actually in PhD in, I think, in physics, and in, undergrad in physics, PhD in aerospace, working on satellites. And then decided that satellites were kind of boring, and went to do a postdoc in robotics at Harvard, working with Scott Kindersma. From there, went to Stanford in the aerospace department. Went back to doing some more satellites and some robotics all at once, which is a really neat mix, and is now at CMU. I've always really loved Zac's work, particularly the way he's sort of able to fuse really principled, kind of deep insights on optimization with domain-specific, expertise on the robotics side or on the aerospace side. So I'm super excited to see what he has to say to us today. Thank you for coming, Zac.
Thanks, Michael. And yeah, thank you guys so much for having me. It's great to be here. Right out the gate, I'd just like to say, please, I hate monologues, so please feel free to yell at me and interrupt me, and that's always more fun, I feel. So, I mean, obviously you can hold your questions to the end, but it would be a lot more fun for me if we had a bit of dialogue. Okay, so as Michael mentioned, I have had a long-running interest in space things and still do. In fact, I'm not going to talk about it today, unfortunately, but we have 4 satellites on orbit from my lab right now doing kind of crazy multi-agent formation flying things. I'm happy to talk about that later if you want to, but just to kind of bring it back, as a space nerd, this is one of my favorite robots, right? This is Mars Curiosity. This thing it's kind of incredible. It's been on the surface of Mars for 11 years now, which is wild, and still operating, right, in one of the harshest environments imaginable. And this thing in that time has covered 31 kilometers, which sounds really impressive until you divide those two numbers and realize that's about 7.5 meters per day. So like, here to the other side of this room maybe is about all the distance this thing covers in a single day. And the reason for this is actually this thing is pretty much not autonomous. Like there's some amount of autonomous driving these guys do, but for the most part, the way this thing is driven, does anyone know what this is? This is the famous Mars yard at JPL, where I have been lucky enough to visit a couple times. So what's going on here? They have basically a mock-up of the rover in a big sandbox with a bunch of rocks and things around. And to figure out how to drive this thing, there's a bunch of human drivers that go in this giant sandbox and move the sand around and move the rocks around to recreate the scene as best they can around the rover on Mars. And then they painstakingly plan and drive around these things to figure out how to drive in the given scenario on Mars, and basically uplink these things, and the rover executes it. So it's kind of a painstaking human-in-the-loop situation anytime they come across anything tricky. And as a result, right, you're ultimately not able to cover as much ground, get as much science done, et cetera, et cetera. And then kind of, meanwhile in robotics, right, we're all familiar with seeing like really impressive feats on legged robots. But I think for me, this is still the bar, and we're still not quite here. But like what we'd love for these systems to do on Mars, say, is to kind of operate with the level of agility, robustness as these guys are able to, right, on super rough terrain, reasoning about full body dynamics, rich contact interactions with the environment, all that kind of good stuff. All right, so how are we going to do this? I guess this talk has kind of 3 parts. And it's a bit of my philosophy on this whole thing, so I guess bear with me a bit. So part one is everything is optimization. And this is kind of my take on almost all of the, say, sub-problems you might care about solving as part of a stack to do this sort of thing, at least can be and maybe should be posed as an optimization problem. So some of these we're all familiar with. The first one being control. So we're all familiar with optimal control, reinforcement learning, right? And the gist of these things, right, is maybe you have a model, maybe you don't if you're doing model-free RL, but you have some model of your robot maybe with things like F equals ma and torque limits. You have some kind of objective function, cost function, reward function, depending on if you're a learning person or a control person that you're trying to maximize or minimize that kind of encodes the behavior you want, right? Maybe things like minimize effort, get to some goal, minimize time, whatever that might be. And then, generally speaking, we can discretize this and throw it at a computer in a bunch of different ways and hopefully get an answer out. Almost identically, right, we're also probably all familiar with the fact that state estimation can be posed as an optimization problem. As a fun aside, it's actually equivalent to an optimal control problem in a bunch of interesting ways. But similar deal, we can solve this optimization problem and figure out where we are, given measurements in a model and all that good stuff. Maybe a little bit farther afield and less familiar to us in robotics is that you can also pose physics as optimization. And probably a lot of us have heard of this. This is the classic least action principle. Usually we encounter this like maybe somewhere in our undergraduate physics, and it's usually this weird thing involving calculus of variations that we'd rather forget. And somewhere in there you end up with like the Euler-Lagrange equations, and then life is good, and we kind of use some package to just like give us the manipulator dynamics. But I think there is actually a lot of value in going back up to this slightly more abstract optimization formulation. And if you take this kind of a little bit more seriously, there's some particularly useful properties for us in robotics here. So if you kind of take this formulation seriously and rather than do the kind of crazy calculus of variations things and get your Euler-Lagrange equations, but instead look at this and try to directly minimize it. Oh, I should mention, yeah, okay, sorry, I don't have the preview thing up here to pace myself. So this, if you haven't seen this, right, this is the L in there is the Lagrangian that we're connecting my exponential entry, and this is the posed trajectory, and you minimize this thing over time. But if you stare at this and think about it for a second, this looks exactly like that optimal control problem, just with some letters changed around. And so if you take that seriously and use the kind of methods we use to solve optimal control problems on a computer, namely we like just discretize this thing and minimize it explicitly as a numerical optimization problem, you can get physics this way too. This is a cool idea. This is not an original thing for me. This idea dates back to the early 2000s from Jerry Marsden at Caltech and his students. And this idea is called discrete mechanics. They did a bunch of cool things with this and proved that you get really nice things like energy and momentum conservation kind of for free by doing the physics this way. Yeah. I have not. That is coming. That is, yeah. No, that's the whole point actually. Okay, so check this out. If we want to think about the environment now, the reason to do it this way is now I have this numerical optimization problem. I can throw inequality constraints in there, and it's no big deal. And we have great solver tools for doing this. In particular, if I want to think about impacts, which historically are these like nasty, non-differentiable, stiff, whatever, things that are hard to simulate. Well, if I take this perspective, all I need to do is throw an inequality constraint on there that says, for example, the height of this brick has to be greater than or equal to 0. If I do this and take that discretized least action problem and just solve it with any solver you want, out pops impact dynamics for free. There's no kind of numerical badness. And it does the things you expect. Basically, if I put that constraint in there with a Lagrange multiplier, the Lagrange multiplier ends up pretty much being the contact force, the impact force, normal force, whatever. And you can do a bunch of cool things with this. So maybe it's a good idea to go up a level and think about our physics in this kind of optimization way too. Similarly, yeah, the friction story, right? Probably you guys have seen this. If you haven't, this is the maximum dissipation principle. Turns out this is a pretty standard way of getting Coulomb friction. What it says is the friction force, which in here is B, that Coulomb friction gives you is the force that minimizes instantaneously the energy dissipation. So that's kinetic energy, right? And subject to this cone constraint here, which is called the friction cone, the thing on the right-hand side of that inequality is mu is your friction coefficient, lambda is your normal force that came from the last problem. So this is a nice optimization problem. We can solve this. We get all the stick-slip nastiness that tends to mess us up and like gets approximated in all these simulators we're used to using. This just gives you the answer, and it's a convex optimization problem. So why is this, so hard? And the last one I'll talk about, which is actually recent-ish work out of our lab that I'm particularly proud of and I think is kind of cool. Collision detection is also maybe a good idea to pose as an optimization problem. So you can kind of wave your hands and imagine if I'm looking for the closest point between two convex objects, I can pose that, distance is a convex function, right? Some kind of norm. If they're convex shapes, I can kind of write this down as a convex optimization problem, find the closest point in the distance between the two objects. There's some details in there. I'm going to kind of skip for now, but there's a paper on it. It's kind of cool. And yeah, we can do this as an optimization thing too. So what we've kind of gotten to here is, we've got physics, we've got collision detection, we've got state estimation, and we've got control. All of these are optimization problems at some level. And kind of the key question now, which is part 2 of the talk, is how do we put these things together and kind of assemble them? And really what's going on here, right, is all these things, they're all nice little optimization problems on their own, but they're all tightly coupled. They all depend on, the solution to one depends on the solution to the other, and they're kind of nested in this very funky, weird way. So what we're going to try to do is come up with a good way of algorithmically, numerically attacking this kind of nested web of coupled optimization problems. Before we get into that, though, I wanted to just take a brief interlude through contact dynamics and control for these things and why this is hard and why this is a thing if you haven't done this before. So this is that optimal control problem we saw before. The problem is if we want to apply it to something like this legged robot here, we run into issues with differentiability. So these impact things and also stick-slip friction, right? These are all non-differentiable things. And you can try to approximate these in various ways, but you end up with generally bad numerical things happening due to this non-differentiability. If you try to do anything with gradient-based optimization here, right? And so in particular, right, that dynamics function there for this robot, if you're not doing some sort of relaxation, whatever is non-smooth, the gradients are kind of bad in various ways, and it makes doing gradient-based optimization really hard. That said, right, we're all used to seeing robots do pretty impressive things. So how does this get done? Practically speaking, most of the robots out there today are doing some kind of hybrid approach. What this pretty much means is if you can look at this problem and pre-specify the contact, what's called the mode sequence. So for example, for that legged robot, it's the ordering in which the feet touch down and lift off. So basically the gait. If you can pre-specify essentially when those things are going to happen, these are called mode switches, right, in the parlance. You can essentially remove those nasty non-differentiable switching events from the optimization problem entirely. You kind of pre-specify them, and then you're just optimizing over those nice smooth arcs in between, and we're back to stuff we know how to deal with. So this is pretty standard. You can use standard tooling. We can solve this, in ways that are fast and accurate. The problem is we need this contact mode pre-specification. In a lot of cases, you can do this kind of reasonably, in particular in a lot of locomotion contexts where you can just pick a gait, especially for a biped, right? It's like left, right, left, right. There's not too much to do there. Even for a quadruped, there's a handful of gaits you might want to do, and there's lots of good heuristics for doing this. So you can get pretty far with this. And so, we're all used to seeing this stuff. I'll, tease this briefly. This is really impressive. This is all done with kind of these hybrid ideas. But there's some issues, even in this context, with these ideas. And we're all used to seeing these blooper reels, too, which, to their great credit, Boston Dynamics puts these things out. But if you look critically at these, there's some pretty glaring things that I think are actually really this in particular, right? So what happened there? Basically, the robot's trying to like jump over this beam, and it's making contact with its hand. But then in the middle of the maneuver, it grazes its foot and then fails, right? And the reason it failed is that it was relying on this pre-specified contact mode sequence that said only the hand was going to be in contact with the environment. And the controller, as a result, didn't have any way of reasoning about the contact forces made by that unplanned foot contact. Said another way, the controller is essentially open loop on the contact modes. It cannot reason about unplanned contact switches. And so this makes these things kind of, in some sense, inherently brittle. And you can imagine putting these things out into the wild, not in a nice lab environment like this, you can get into serious trouble. So there's kind of this open loop nature to the contact modes, right, that we'd like to try to make our controllers reason about more fully. The other scenario in which these things tend to break down is when you have lots and lots of possible contact modes that you have to reason over, which can happen pretty quickly in manipulation tasks where you might be, say, doing in-hand manipulation, and you can't just talk about a handful of a finite number of contact points anymore. It's like a continuum. If you tried to discretize it, it'd be very high dimensional, and you'd end up with combinatorial badness trying to figure that out with a hybrid method. So that's the hybrid story. What we're going to try to do is this second thing here, contact implicit is what this tends to be called. And Michael here has done lots of this and kind of pioneered this in some ways as a PhD student. And the idea here, though, is what we really would like to do is optimize over not just the state and input trajectory of the robot, but also these contact forces, and let the algorithm fully reason about the ability for the robot to make and break contact with its environment and deal with unplanned contacts and actually plan these contacts itself. So far, though, most of the methods that have kind of tried to address this, they either make a ton of approximations, basically smoothing approximations for these contact physics to make the derivatives nice, or if they try to kind of really deal with the true nature of these kind of discontinuous stiff contact things, they tend to have serious numerical difficulties or combinatorial blow up in some way, right? Okay, so that's what we're after. Back to this thing. So what I'm going to do now is kind of tell you how we're going to try to take all these pieces, which we, in principle, each one have a nice optimization algorithm for, and stitch them all together in this kind of weird coupled diagram. Yes, please. No, it's great. Yeah, I think we can do it. Yeah, I think there's nothing stopping you from doing it. I mean, yeah, there's the Rayleigh dissipation function, right? You can state friction in a variational way. It's sort of it's all optimization, right? So it comes down to this like, yeah. So we're going to try to fit all these together right here. All right, so the trick is, for each one of these, I have a nice optimization formulation that I know how to solve. So right now, it's about the trick of how to hook these together. And the key idea here is what I'll call a differentiable interior point method. There's like a bunch of details in here that I'm going to kind of gloss over pretty quickly. But the idea here is let's zoom in on one of these blocks. Inside one of these blocks, I have a nice little optimization problem. I'm going to focus on this inequality constrained thing, try to keep it nice and simple. Imagine for now, this is the impact dynamic. So it's that least action problem, and that inequality is, hitting the ground. If you're not familiar with interior point methods, the essential idea is I take this set of inequality constraints and I put them in the objective with this log, what's called a log barrier. And what that looks like is this. So you have this log function that basically blows up at the constraint boundary. The key idea, though, is that log function is analytic. It's smooth. It's got all the derivatives you want. And you can kind of tune its smoothness with that row out front, which is called the central path parameter or the barrier parameter. And this is how this is basically how state-of-the-art, say, small to medium scale convex optimization solvers work. So if you've used CVX or any of these things, this is what's going on under the hood. There's decades of theory behind these things on how to make them converge. Essentially, what happens is you start with a relaxed row where it's nice and smooth, and then you take some Newton steps and crank down row until you get an answer that's sort of the true hard answer to whatever level of precision you want. And again, there's good theory on how to do that cranking, how to make sure the numerics stay nice, and if the problem's convex, there's all these nice guarantees that you'll get the answer you're after, right? Okay, so the key thing, though, is that log thing is basically relaxing that stiff, hard inequality thing in such a way that you can take derivatives through it, and at the same time, though, still crank it down in such a way that you recover the original answer doing gradient-based optimization. So we're going to do this. If I now take that log barrier thing, that whole thing, and essentially write down, gradient equals 0 and whatever Lagrange multiplier stuff, right? These are called the KKT conditions or first order optimality conditions. I turn it into basically a root finding problem over there, that like R of X and Y equals 0 thing. I should say what I want to do here, right, is I'm minimizing this problem over X. So maybe for a second, we'll think about, we've got this, the impact least action problem over here that we're trying to solve. We've also got, say, the Coulomb friction problem. Remember, the Coulomb friction problem depends on the normal force, which is coming from the solution to the least action problem. So that's how they're coupled, right? So let's imagine for a second, we've got the least action thing. It's solving for, say, normal force and pose, but it has an input to it, which is the friction force. It's not optimizing for the friction force, but it's an input. So in this context, right, for the least action problem, X might be normal force and pose. Y might be the friction force that's coming from the other problem. If we go over to the friction problem, that maximum dissipation problem, it has the normal force as an input, but it's solving for the friction. So in that problem, it's optimizing for friction. So the X might be the friction force. And the Y, this problem parameter that affects the solution, but is not an optimization variable, it's a parameter, would be the normal force. So that's kind of what's going on here. So I can get the solution to this problem by basically writing down these gradient equals 0 things. But what I would like to do here is then actually get the derivatives of, say, X with respect to Y at a solution. We know how to do this. This is called the implicit function theorem. It's not such a big deal. You basically take dr dx, dr dy, and move some things around. And as long as that Jacobian in there that you're inverting stays full rank, which it does under certain regularity conditions, you can compute dx dy from this thing. And so if I take all that together now, if I have a solver, and I have this implicit function theorem trick. The other thing that's worth mentioning, by the way, is that Jacobian inverse there that you need, you actually get for free when you solve the original problem. Yeah. So yeah, those are the gradient conditions. Yep. So yeah, in general, I can actually. So pick your favorite one of those problems. I mean, we can talk about this in more detail maybe in a minute when I get a little further along. But generally speaking, all those individual problems I just showed you are super well behaved and super nice. The least action problem, it's basic physics. It turns out locally that problem's convex. Guess what the Hessian of that thing is? It's the mass matrix, right? The mass matrix is Hessian of Lagrangian. So that's super nice. Oh yeah, no, it totally, this all checks out. As long as you're essentially the Hessian of the Lagrangian, the dynamics Lagrangian with respect to the velocities is the mass matrix, right? So that's kind of what's going on here. The potential function shows up actually in the KKT sort of like AX equals B thing. The potential is showing up in the B vector on the other side. So okay, so the dynamics Hessian is super nice. It's essentially your mass matrix. So as long as you don't have a weird perverse thing that you write down, that's guaranteed to be positive definite. And then yeah, like the collision problem, it's basically like identity flavor. It's a norm thing. The friction problem, that's a second order cone. That thing actually doesn't really have a Hessian, but it's a convex problem. We know how to solve those. Yeah, so pretty much all of those are reasonably well behaved on their own, right? And the problem is hooking them together. That's kind of the key idea here. So I guess what I'm telling you here, yeah. Yeah, I hate this question, but I'll take it. That is a pedantic sort of thing that is true in weird edge cases, but not true in general. For short time steps, yeah, so if I take, so where that happens, to be clear, I get this all the time. In fact, I get it from reviewers and it's just wrong and it bothers me so much. So I would love to address this. Basically, if you take a short enough time step, like if you take the limit of delta t really small, you're basically, you can think of it as for short delta t, you're back to the continuous problem. For short delta t, the Hessian there is the mass matrix, which is guaranteed to be positive definite. So there's a sense in which that problem's locally convex. It kind of has to be, right? It's physics simulation. We know how physics works. Basically, it has to be solvable for the next time step. So the idea there is for short time steps, it's just the mass matrix and it is positive definite. Where the saddle point thing comes up is if you take long trajectories, that thing can become a saddle, but we're never doing that. And so there's some nice results from the Marsden, discrete mechanics stuff where they basically prove that for sufficiently short, essentially if your delta t is reasonable, it's pretty much guaranteed to be convex. You can end up in weird bad situations if you make delta t too big, which is kind of obvious that's going to happen anyway, right? So okay, yeah, sorry if I was like a little aggressive about that one, but it's yeah. Okay, so that's so I guess the upshot of this, given that I can do this, essentially what I can think about now is this optimization problem. If I write down a nice interior point solver for it and play this implicit function theorem game, I can stop thinking about it as an optimization problem and think about it as just any other differentiable function. I can evaluate the function by solving the optimization problem. So I can get x as a function of y for some given y, right? And then I can also evaluate dx dy, its first derivative. It essentially doesn't cost me anything extra if I'm already solving this problem because that Jacobian that you have to invert there is the one you're actually using inside your Newton solver anyway. So I solve this thing with Newton's method, I get the x value and I get the derivative essentially, as kind of a one-stop shop. And I can just think about this as any other function. This also not new, by the way. People have been doing differentiable optimization. It's kind of been hot recently in machine learning with like these convex layers ideas. They're not doing it with this interior point stuff, though. They're doing some slightly different stuff because they care a lot less about nice gradients, and they're willing to take like messy stochastic gradients. OK, so stuff you can do with this. One thing you can do is put these blocks together and make a simulator that sort of has impact dynamics, Coulomb friction, and this collision stuff. We did this a couple of years ago, called it Dojo. It has some cool things that I would like to highlight. The first is that you can do kind of true hard contact simulation. In particular, if you're familiar with other simulators like Mujoko, these often have weird artifacts. In particular, they have interpenetration, say, where the feet sink into the floor. They also have creep, which means because stick slip is inherently non-smooth. So if you do any kind of smoothing, you can't actually do sticking friction. So if you're in Mujoko or many of these other simulators, you always get creep. You basically always get stuff slightly sliding downhill, and you can't get true static, like sticking friction, which is annoying. I mentioned briefly, and I'm not going to go into it, unfortunately, but like this kind of variational perspective where you're minimizing that action integral. These methods in conservative settings, they give you energy and momentum conservation basically to machine precision, which is very cool. So they have these nice long-term stability properties. They obviously don't conserve energy in this impact friction setting because it's not conservative. But the point is they give you good long-term stability, which is really nice. And then finally, we can do all of this while still giving you smooth gradients for downstream optimization, which sounds weird and sounds like getting your cake and eating it too. But there's kind of a key trick there that we're playing. I mentioned this rho parameter, this central path parameter that's kind of smoothing things out and lets us take gradients and lets us do Newton's method. So with this setup, what you can do, so these pink lines represent iterations of the solver where I'm iteratively cranking that rho down. And you can see as I crank rho, it gets stiffer and stiffer and kind of eventually converges to the true kind of hard answer for these like kind of stick slip and impact cases for a block. So what we can do here is if we cache the iterates of the solver, we basically got this library of smoothed solutions for various values of rho. So I can simulate the hard contact, which would be the black line, and return that as the state, say at the next time step. But if I basically return any one of my previous iterates, I can return you the gradients or the Jacobians of one of the previous iterates, which gives you a nice smoothed out gradient. And you can pick which one you like. You can pick the degree of smoothness of your gradient. Yeah. Because I'm actually simulating the black line, but I'm giving you back the gradient for one of the pink ones. So you can have whatever pink gradient you want while still having, so one way to think about this, you're using an approximate gradient, but you're using the real physics solution, right? So I can give you x k plus 1 with no creep and no interpenetration, but I can give you dx dy for one of the pink lines that's smoothed out. Yes, we are. So what I'm doing is basically caching say the last 3 or 4 iterates of the interior point method. I'm giving you x from the final converged answer, but I'm giving you the derivative from one of the previous iterates that was smoothed out before I pushed rho all the way down and converged all the way. Does that make sense? I mean, machine precision is in I can solve this to like full double precision. So it's as good as anything you could ever hope for, right? Like I can give you the real answer. In fact, if you really want like what you can do, right, is like at the end of this, I can do a solution polishing step where I fix the active set, which we do sometimes. But you can basically converge to whatever level of tolerance you want and get the real answer, right? Yeah. Sorry for the letters. These are supposed to be forces. So this is a brick falling vertically, and that's the force F. And this is showing you when you hit the ground, you're getting this like, discontinuous jump in the end. Sorry, yeah, for the not explaining the letters. So yeah, I guess this is kind of a subtle point, but the way I like to think about this is I'm giving you the real answer, but I'm giving you a smoothed gradient. And I can give you both of those things. And you can still do useful things in this in the same sense that we do quasi-Newton methods all the time, or we use stochastic gradients all the time, right? So the gradient might not be exactly the gradient for the solution I'm giving you. It's a closely related thing, but it still gives you informative information on where to push your solution. So there's many ways of doing quasi-Newton stuff. What I mean there is specifically just that you can still converge to the exact solution in those methods in spite of errors in the Jacobians that you're using. And there's all kinds of nice theory about basically if you can bound the error in the Jacobian, you can sort of still get superlinear convergence, for instance, in these methods. So you don't need the exact derivatives to get the exact solution, is kind of the main point here. I suppose, like, in the sense that there's some, it depends on how you define the error. So I think I could easily write down some error metric that's the distance between one of those pink lines and the black line, which is kind of in the spirit of stuff you've done. That's right, yeah. If it's truly non-differentiable, that's right. I couldn't, yeah, 100%, I agree with that. Yeah, so there's a lot of weird, subtle aspects of this. So here's a fun one that I really want to dig into for a minute, though, that I think gets at some very deep kind of stuff. So if you put this kind of like, so here's a couple of blocks, I'm dropping them on top of each other. If you do kind of more or less standard simulation stuff, you get something that looks like what's on the left there. So what's going on here, if I have a collision detection algorithm, so if I'm in a traditional simulator, like this might be something like GJK, that's trying to find the closest point between two objects. If I use that algorithm to give me the closest point, and then I plug the closest point into my simulator, you get behavior like on the left there. And what's going on there is basically the fact that if I ask you for the closest point between two blocks that I'm dropping on top of each other like this, it's ill-posed. Because it's basically pick any point you want on the surface, right? It's sort of underdetermined in some sense. So what a generic GJK implementation might do is give you the centroid, which is completely reasonable. Essentially what it's doing is regularizing and giving you some unique solution because there isn't a unique one. But if I just take that in kind of an open loop way and plug it into my simulator, I don't get realistic dynamics. It's giving me the centroid, which now like makes the blocks. So I can't really balance these things on top of each other unless they're just right, perfectly lined up, right? So we're going to call this weakly coupled. I stole this lingo from the finite element and CFD communities, which is how they talk about this. So this is what happens if you kind of do it that way. What's going on in Dojo, though, we're doing what we call a strongly coupled method. So we're doing that in that diagram up there, we're simultaneously solving jointly the collision detection problem and the physics problem. And those things are coupled in the solver at this very low level, and they're being jointly solved. And so what's going on there at a high level is, in this, if we decouple these problems, I don't have a unique solution. I pick some regularizer and that's it. Yeah. No, not in this case, because it's two flat faces. That's the problem. If I round the faces, you're saying. I think it'll roll off then. So here's what's going on here, which is fun. So here, okay, the closest point problem is underdetermined, ill-posed, where it doesn't have a unique solution. But if I stack these things and solve them jointly, that least action problem is basically minimizing energy. And that minimizing energy term, when you couple them, regularizes the closest point problem and picks the closest point that minimizes the energy. And so that gives you kind of the obvious physically realistic behavior that you see there. It chooses the closest points on the faces that's going to minimize the action, which kind of makes all the sense in the world and is kind of what you want, right? So this is kind of the math version of that story. If I have, so the way we actually do this in all the methods I'm showing you, we're taking these, say these two blocks, we're writing down their optimality conditions. So the R that we talked about before that has to equal 0, that's that gradient equals 0 kind of thing, right? Plus Lagrange multiplier shenanigans. And I'm doing that for all the blocks, and then I'm stacking their first order optimality conditions. So these are coupled, right? So in the first one, I'm minimizing over X, and the second one, I'm minimizing over Y, but they both depend on each other in this weird way. But I write down those gradient equals 0 conditions, stack them all up, and then set the whole thing equal to 0. And I jointly solve for both X and Y on this whole thing. This is a weird thing to do. To be clear, this is not anything a standard off-the-shelf optimization solver does. This is, for me, this is like kind of one of the core composable, what I mean by composable optimization is this idea of like, I'm solving these in a strongly coupled way simultaneously at the same time with all the coupling in there. And this has, so this is closely related to actually ideas from game theory, if you want to dig into it. This is kind of, this is a weird instance of what might be called a generalized Nash equilibrium from game theory. So these, I would say this whole idea sort of is in some sense a generalization of ideas like Stackelberg and Nash equilibria from game theory and stuff like that. But these are the core ideas, like you're stacking the optimality condition for all the problems and getting all that cross coupling and then jointly solving all those optimization problems. Yeah. It's really hard. This is a big, nasty, sort of, I would say, okay, so maybe one way of saying this is there are not standard tools to solve this problem. I cannot take this and throw it into IPOpt or CVX or anything. The effort that we went through to actually solve these things was like implementing all of the optimization solver tooling at a very low level, as in we wrote our own like custom sparse linear system solver kernels and like all the details, which I'm glossing over a lot about how you make interior point methods work. One of the key things there is line searches and what are called second order correction or predictor corrector methods. The key issue there is in that log barrier, it's differentiable, but it blows up to infinity. So you can't step across the barrier. Things blow up, right? So in interior point methods, one of the key ideas is that you take a Newton step, which is using a linearization. Usually that Newton step steps across the log barrier. And you actually have to do fancy line search techniques where you backtrack till you're back in the feasible set. And then in order to actually make progress, that tends to ruin your convergence. So then what you do is this kind of predictor corrector step where you backtrack till you're back in the feasible set and then take a step that's sort of parallel to the boundary to keep making good progress. So there's a lot of details in making interior point methods work on nonlinear. In fact, I would say like interior point methods apply to nonlinear problems didn't really get figured out until the late 2000s. So like in some sense, the basic tooling to just solve one of these blocks for a nonlinear problem didn't get figured out till like 2005, 2007 or so. And so what we're doing is an even weirder, nastier thing that's kind of fundamentally hard at a numerical optimization level. And there weren't previously good tools to do it. So I don't know if that answers the question. I mean, yeah, I don't know if that's a good answer or not. Like maybe this is a dumb thing to do and I'm the ignorant one. I don't know. Yeah. Oh, sorry. Yeah, I think like doing it without inequality constraints has been done quite a bit. And these are Nash and Stackelberg equilibria from game theory. So that in economics in particular, people have looked at this stuff, but I'd say there hasn't been a real push to make high performance numerical solvers that can take problem instances of this form with all the constraints in the subproblems and solve them nicely. Yeah.
So it seems like it's might be obvious, but it seems like here you have these two top optimization problems. You can turn them separately into the root finding problems. You root find join, and it seems like maybe the key idea is that you're not turning it into one optimization problem and then root finding that. It's not going to be
That's yeah, because of this picture, basically. If you solve them separately and try to like pass information between them, you're going to get the answer on the left.
Like why can't you write this box on the slide? It's one big optimization problem.
Well, okay, so what kind of optimization problem would it be? The answer is it's this optimization problem, which is a very weird optimization problem. This is not a standard form nonlinear program or any kind of convex problem. This is a weird problem that the closest thing to this is something called a generalized Nash equilibrium, which is something in the like kind of behavioral economics literature. It's a very weird problem. Yeah, it's a very weird, so the KKT conditions for this are some kind of like variational inequality. Like, yeah, you could probably call, another thing you could call this is a mathematical program with complementarity constraints or equilibrium constraints, but I think that viewpoint does not result in good algorithms. Because what you're trying to do there is think about it at the level of like complementarity constraints, which are horrible things that you don't want to deal with. And I think the lesson of like kind of numerical optimization writ large is every performant optimization algorithm finds some way of sidestepping complementarity. In interior point methods, you smooth it with a log barrier. In active set methods, you switch to avoid dealing with it. Like kind of every way that we know to solve optimizations well is basically like a trick for circumventing directly attacking complementarity. And so pick your favorite way to do that. Yeah, sorry, this got pretty. Let me try to get us back on track. So yeah, you can do cool things with this, with the gradients. This is just kind of the point that like, okay, so there's one of these is doing like ILQR, one of these is doing some sysid, trying to fit the parameters of that box from data. The middle one is like the half cheetah OpenAI gym example where we're actually just doing gradient descent instead of weird stochastic RL things. And the bottom one is doing some sample-based planning stuff using the gradients. So you can do useful things with these smooth gradients is basically the message there. Okay, so then to kind of finish up here, like the stuff that I really want to, I guess, talk about that we've done in the lab is now taking all that physics stuff and then nesting it or combining it with the optimal control problem and doing sort of the stuff in these videos. So we went pretty deep on this. As you can imagine, like, again, these optimization problems are not easy to solve. The numerics are pretty gnarly. And so we started asking the question of what in this could we approximate while still maintaining the ability to reason about these kind of contact interactions in a nice way. And so what we started doing is we want to keep, and another way of saying that is we want to keep the structure of this problem. We want to keep this block structure with this cross coupling, because this is what's giving us the ability to think about stick slip and impacts and all this other nice physics, right? So what we're going to do is keep the structure, but start approximating things in the boxes. And so in particular, for this control problem, what we're going to do is say, take a reference and track it. So now we have a nice quadratic objective that's nice and easy. Inside the dynamics, what we're going to do is linearize the dynamics locally about some nominal trajectory, for instance, or some nominal pose. Again, we're not linearizing anything about the impact dynamics. We're just linearizing the manipulator dynamics, if you like. In the collision stuff, we can linearize the sign distance function about some reference pose. So again, it's not keeping the problem, but we're making the problems easier, right? And then similarly, the friction cone, we can approximate, which is a standard thing, using a pyramid if you want to. That one's less critical, actually, but so you can kind of approximate stuff in the boxes is the message to make this, but you keep the structure, right? And then you can do cool things. So this is a fun little example we cooked up that we call PunchBot. It's an inverted pendulum with a little like kind of arm on the top. And the setup here is you linearize this thing about the upright, unstable inverted pendulum equilibrium. And that's it. You linearize everything there, sign distance, manipulator dynamics, whatever. And then you whack it. And it has no information a priori about any kind of contact modes or anything like that. And it just figures out, how to reach out to the left or right and push against the walls to balance itself. So it's doing kind of very explicitly this kind of contact mode planning, right? And it just comes out of that optimization setup. And we can solve this really fast, I guess, and it's all that linearized stuff. This is one of my favorite examples that I think really gets at the true power of this. To me, this was wild when we got this to work. So this is a sort of very cartoony model of a quadruped that we call the point foot model. It's a single rigid body for the body, and then point masses for the feet. And it's sort of easy to write down. So we're basically abstracting away the leg kinematics, is another way of saying that, to make the dynamics nicer. And what we did here was take this, have a nominal trotting gait, trotting in place at the origin that we linearize about. So you have this linear time varying kind of thing. We're just trotting in place at the origin. That's all it has. So it's linearized around that and just doing MPC on that. And then we just kind of kick the crap out of it. And it flies through the air and flails around and lands somewhere over there and trots back to the origin. So it's flailing around. It does effectively push recovery, figures out where to place the feet to not fall over. And then it's somewhere way over here. And it just nicely trots back to the origin. All we gave this was, again, a linearized set of dynamics and contact sign distance function information for this trot at the origin thing. And it figured all that out, kind of in like this emergent way. For me, this was kind of the really impressive thing that like initially doing this in sim made me believe in this, that we could really do some cool things. Yes. Yeah. So that's coming next. Thank you. So we've done this on hardware. This is now kind of a little outdated. We're continuing to push this stuff. So this is on hardware. We're running the controller at around 100 hertz, which is not fast by kind of modern, say, QP, MIT Cheetah standards. And these demos are not particularly impressive by those standards either. But this lets you do weird stuff, right? So if I wanted to just trot, I wouldn't do this, right? I'd do, pick your favorite variation on the, like, say, Cheetah controller that's doing hybrid stuff with a gate. But we can do weird things like we can reason about arbitrary contacts with the body in arbitrary ways. So this we're like, using contacts with the head and like the other parts of the body, right, with the environment in kind of interesting ways. And so I think this opens you up to, this is pretty preliminary stuff. We're kind of actively working on some demos of this flavor that I don't want to give away because I think we're very close to getting them to work. So they're going to be cool, I promise. But yeah, so this gets you this ability to reason about arbitrary contacts, right? And I can get this stuff without having to do a whole lot. I can linearize the sign distance function for this guy standing in the corner, and it can now know, oh, I can stick my head in the wall, I can like do all this weird stuff, and it can kind of generate those. So they're time varying linearizations in these tracking problems, but I mean, it's a weird, calling them linearizations is a bit funky, and yeah, I sense the discomfort with this, and I agree. It's not, though, a piecewise hybrid thing. What I'm doing is keeping this weird optimization problem structure, this block structure with all these weird cross-coupled optimization problems, and say, for instance, rather than that least action problem being a nonlinear, nasty optimization problem, I make it a very benign QP, for instance, right? So I'm taking all those subproblems that might have been harder. So the geometry, you mean? I guess, what do you mean by boundaries? The geometry in the environment? Yeah. So that's in the sign distance function. So there's they're time varying linear. They're not really piecewise. Like yeah. So we're linearizing. It depends on your definitions here. I guess there's some semantic thing. This would be much clearer if I just wrote the math out, I suppose, which we could do later if you want. But I guess another way of saying this. So I have this. We've divided this thing into a bunch of bodies, right, in that collision problem. So I have a body for the head, I have feet, and right. So I stack all those up, and then I solve that sign distance function problem. So it's like, what's the closest point to the environment, blah, blah, and I linearize that thing. So you're right that this has this kind of piecewise linear flavor in that, like, the closest point at some point will, if I move the foot, it's going to switch from being here to here. But if I do this in a time varying way, that just kind of shows up in, if I have a Jacobian, like basically that phi of q function becomes, some Jacobian whatever, and that is time varying. And so yes, there's some implicit switching, I suppose, going on in that time varying thing. For me, the key thing about this is we're not doing switching. There's nothing hybrid about it. But yeah, you're right in the sense that those Jacobians at some point are switching. Yes, so yeah, I think that's right. As a function of time, there are definitely discontinuities in these things. Yes, I think that is completely fair characterization. Yes, but I'm not doing mode enumeration, though, I guess is the thing that I want to make clear, right? Like, it shows up there are complementarity things in the KKT conditions of all those subproblems. And we're keeping that in there and solving those problems. Yeah, this might be a little, let's definitely follow up on this, though. Yeah, I'm happy to do that. Maybe I should wrap up, right? We're getting close. Okay, so let's wrap it up. So part 3, what else can we do with this stuff? So I alluded to the group theory thing. Game theory thing. We've actually done some of that. We've have a couple papers doing weird game theoretic MPC for autonomous driving that basically uses these ideas and sets up kind of multi-agent non-cooperative games to reason about other drivers for like weird highway merging examples. Again, sort of along the same lines as the game theory thing, like mini-max problems that we're familiar with maybe from robust optimal control are also instances of this idea, right? We can just explicitly write those things down and couple them. And so that's an example of a toy problem where we did some robust control stuff on the right. Other things we've messed around with, we're kind of starting to get a little bit into manipulation. This is some recent dish work from one of my students who's been doing this in collaboration with some Google folks, where the fun hook here is we have this thing that can reason about collisions or sign distance, whatever, for convex bodies. And in a lot of cases, traditionally, what we do is use point feet on the robot and have like convex decompositions for the environment. But for me, that makes little sense in the sense that we already know the robot geometry a priori. So it'd be easy to write a convex decomposition of the robot down once offline. But I don't know the geometry of the environment. So what's going on here is we're actually taking a point cloud. We have this weird non-convex bunny thing that we're trying to manipulate. And I want to reason about its geometry. Figuring out a convex decomposition or a meshing of that thing online, to me, seems kind of hard and bad. But I get point clouds from my perception system. So what we're doing here is representing the geometry of the bunny with a point cloud. And then the robot gripper and the manipulators is a bunch of convex bodies that we figured out ahead of time. The cool part about this is you can parallelize it over the points in the point cloud. So it ends up just being tons of little tiny convex problems, and we can throw those on the GPU. So this was done, we wrote this up in JAX, and it turns out the fun scaling thing here is it takes the same amount of wall clock time to do one point as about 10,000 on a modern desktop GPU. So you can really kind of just throw your point cloud in there and go, which is this thing. We've done a bunch of state estimation stuff too that's kind of fun that leverages some of these ideas that I will not have time to talk about. but I'm happy to do offline. And then one of the big things we've been focused on lately, I mentioned, these problems are big and kind of hard to solve, and it took, frankly, like pretty heroic effort on the part of a few of my PhD students to get the numerics to work well enough and fast enough that we could solve these things in real time. So we're really interested in ways of solving these problems faster as we scale up. And one of those efforts recently was designing a QP solver that's sort of GPU native. And when I say GPU native, not in the embarrassingly parallel, I can solve lots of tiny problems in parallel, but I want to solve, say, the Atlas problem with very high dimensional states. How do I actually do that in a way that exploits parallelism? This is a really kind of hard problem that it's still open. We don't really know how to parallelize large optimization problems, I'd say, for things like this. And so I don't know, the punchline here is we figured out a way to take the sort of ADMM thing that OSQP does and map it into a ReLU network analytically so that we could run on a GPU. That example, that's the full body model of Atlas, solving a reasonable horizon MPC problem running at 2.5 kilohertz on a desktop class GPU. There's lots of limitations to this, but I find that pretty promising and interesting. It's maybe going to let us scale some of these things up. And then I'm also interested in scaling things down. We do a lot of tiny things, it turns out, especially in my other aerospace interests. So another recent paper that I'm pretty into that is maybe a little bit orthogonal to most of the talk, but I want to tease it. We did this paper called Tiny MPC, where we played a lot of tricks and got an MPC solver to run on a tiny microcontroller, so we can run it on things like this crazy fly drone on a little STM32. And then to finish up, I'm also, I guess, really interested, going back to this whole context story, in like we talk about the sim to real gap all the time, and people are into ideas around transfer learning and stuff. But for me, what would make a lot of sense and be really interesting that I think is maybe a bit underexplored right now is, I might do all this stuff and go run on the hardware. Why am I not taking all the data from the hardware and pulling it back into the simulator and doing essentially sysid? But I think we can do this in a pretty general way where we maybe use function approximation or whatever you like in targeted places in the simulator stack, and particular things like this, right? Maybe Coulomb friction's a kind of coarse approximation. Maybe I can learn something there, fit something from data to get a better friction model, actuator models, compliant behavior, all these things that are hard to model, right? I think there are principled ways of targeted function approximation inside the simulation stack, where you take real data on your robot and fold it back in and make the simulator better, so that next time you maybe have to do a lot less transfer learning and you can reduce the sim to real gap. And again, this is possible with the stuff we've got because we can take all these gradients. And I think a really inspiring, maybe body of work recently has been these really impressive drone racing demonstrations. And a big part of that was exactly this. Like they would do a bunch of offline stuff with models, put it on the hardware, take that data, fold it back in to improve the models, like residual learning, and then go back and forth a few times. And I'd say they could do that in the drone context because everything's smooth. But in something like legged robots, I think we haven't quite been able to do this in a lot of these more nasty kind of friction impact cases because of the non-differentiability. But maybe we can do it with this stuff. Okay, and I think I want to briefly, plug all the amazing students who've been doing this with me for the last several years. Many of these are recent graduates or almost graduated. And with that, I'm done. I will shut up. And thank you. Yeah, I love that stuff.
In his planetary setting, where the parameters are really well understood.
Yeah. Which is where I learned it, frankly, in space problems.
The worry here, I mean, you're going to get geodesics or pieces of geodesics, and these are notoriously brittle and subject to large changes with respect to very, very small parametric changes typically. Where is that showing up in the work that you're doing, which seems to be more robust than it ought to be?
Yeah, so we're not really, okay, so I guess I have a much dumber take on the variational integrator thing. So at the end of the day, you do all this work to get to this thing, but the things that actually come out of all that variational integrator stuff are actually just implicit Runge-Kutta methods. In fact, I love that work, so I don't want to downplay it at all. And I think the ideas behind it are super important and deep.
The zeros of your function are done.
Sure, yeah. If you're on the energy manifold, blah, blah, blah. Yeah. So that's totally true in the unforced case. Yeah.
And you didn't, okay, so your point is that
when you introduce the rail idea, you're going to get rid of the.
Yeah, it's not really a geodesic anymore, right? Like I mean, maybe it is on some more weirder abstract manifold that I don't know how to conceptualize, but it's not a. So here's the way I think about this stuff. If you do the variational integrator thing and turn the crank, what comes out, literally the integrators we're using here, we do all this fancy stuff. If you take out the contact part of it and you're just doing sort of smooth dynamic stuff with this discrete variational mechanics stuff, what comes out of it is the implicit midpoint method, which has been known forever. And even all these fancy high order things, you turn the crank, there's a fun way of, so I don't want to downplay the work again because it's amazing. And it's very deep. But the results you get at the end of the day, the algorithm that comes out is just an implicit Runge-Kutta method. In fact, I don't know of any examples where new integrators were discovered this way. What it does is give you, so a lot of these symplectic integrators were known before the discrete mechanics work. I think all of them basically. But what happened was it was kind of a post hoc thing where people wrote these things down and were like, hey, gee, when I simulate this thing, the energy stays constant. That's cool. What's going on? And so they kind of proved the preservation properties in a post hoc way. The variational mechanics thing gives you a constructive method for designing those algorithms from scratch, where you can guarantee that the thing you get out is going to have those properties, which is awesome. But the integrators that come out are basically known methods. Right? It gave us a way to explain things that we were seeing previously. But in particular, the ones we use here are the implicit midpoint method, which has been known forever and has known, right, symplecticity and all these nice things, right, time reversibility. So I guess it's in some sense, it's not a surprise, but I think it's not as weird maybe as and it kind of makes sense, right? Like that essentially what's going on there, right, is like these things, the methods you get out, they're implicit always, and they're always symmetric in time in ways that are like implicit midpoint. You're evaluating things at the midpoint. I can run time forward or backward and get the same answer. So they all have that flavor, but it basically comes out by construction when you do it this way, as opposed to kind of having this hacky post hoc thing. But the real key thing for me here is that we don't actually go all the way down to like the integrator level. We're solving that minimization problem very explicitly as a minimization problem with constraints, which we use, all this other stuff. So for me, that was the key takeaway from that stuff. We don't actually leverage the preservation properties are nice here because what they do is these methods are quite stable, which is very unlike most of the other methods. One thing I didn't mention, that dojo stuff with the atlas falling, we can simulate that at like 20 hertz with perfect stability, perfect, interpenetration, and all this other stuff is perfect, which to me makes sense. The dynamics of that robot are not fast. It's big. It's, rigid body modes are all slow. But if you look at most of the simulators that we use right now, they're at kilohertz rates. And it's because of all the approximations and artifacts and interpenetration stuff. But we can do it at 20 hertz and it's fine. So it's that stability stuff and that time reverse that give you that, which is, I think, still hugely valuable in this context. I don't know if that helped.
Yeah, so I have a question about the real-to-sim work that you were working on. So
I wouldn't say we're working on it. It's stuff I kind of want to do, and I think at a high level is stuff that should be possible.
Well, yeah, so I guess my question can be high level too. So when you have the real-to-sim, so are you trying to, would you plan to use a neural network or the physics model to learn the gap?
Yeah.
If you use the physics model, then there could be something fundamentally wrong about the functional form instead of like
totally.
the parameters.
So I guess what I'm arguing for here is structured learning, right? So it's the idea that like, I know Coulomb friction is bad. So if I wanted to do this, but in particular, if I want to be data efficient about it, right? Because that's kind of the main point here. Is like these experiments are expensive and hard, and also like the models are good enough for a lot of things, but there's areas where maybe the models are bad, and I can know that. I can do these experiments and I can look at the residuals in different places and say, hey, my friction model is really bad. That's the worst part. So maybe it's worth it for me to put a single small function approximator in there in that one spot, which will be a small thing with a few parameters that'll be easy to regress with a handful of experiments with limited data, right? As opposed to learning some big giant residual function on the whole dynamics that's super expensive. So I think philosophically, that's kind of where I'm coming at it from. I want to be able to do this on my robot in the lab in 10 minutes. Once I've got something close, I want to dial these things in a little better based on experience, right? Without having to relearn everything or have some giant thing that requires large amounts of data.
You showed the Stanford bonding thing. Can you talk more about that work?
Yeah. Where'd it go?
What are the difference between the result you show on the two sides? Like,
Oh, yeah, sorry, I really glossed over this, so sorry about that. So what's going on here, maybe we can play it again. This was like very preliminary stuff. We've since done some more on this. If you naively model this as point contact, you get the thing on the left. Basically, there's all kinds of situations, right, where these grippers will grip and you'll get like 1 point over here and 1 point over here, and there's no patch contact stuff there or torsional friction, so it does this. And that's kind of this weird rocking thing, and that's kind of unphysical, right? So what's really going on there is there's small deformation, and like you're getting patch contact effects. And so we're trying to capture that, which is the thing on the right. So we made some stuff up here. It turns out this is known stuff in the manipulation community from a long time ago called the soft finger model. It's basically trying to get at like small deformation, nearly rigid. But essentially what you do is you kind of stick with the point contact thing, but you endow the points with torsional friction. And so that's what's on the right. So what we were kind of showing here is that you could generalize the models that we've got to this like torsional friction, soft contact model thing.
yeah, I think following on this, like there's some argument in the community say maybe everything in the world essentially is not totally rigid, right?
Oh yeah, totally.
And so your work are like trying to deal with rigid and stiff and all these like non-differentiable things.
Yeah.
Everything is kind of soft. Like
I have a take on this also.
okay.
So I guess people talk about soft contact models, especially the Mojoko people, right, have talked a lot about this. And there's a disconnect there. When we say soft contact model, it means something actually quite different from what you're talking about. It does not mean deformation. What's happening in these soft contact models, like in Mojoko, for instance, you're getting force at a distance away from contact. So you're getting weird, unphysical force field kind of behaviors, which is not a deformable object thing, right? That's a very different thing. So I think it's almost like a subtle lie that we've been fed with these lingo is kind of it's a little sketchy, right? So soft contact does not equal some deformable object. It's much weirder and it's genuinely unphysical.
Yeah, I think what I'm asking is like because you're basically doing point contact, and you also mentioned patch contact. I think now there are some similar trying to do patch contact, like
yeah.
Right. So do you think this will be naturally incorporated in your framework, or? Yeah,
you can absolutely do it. And this is like kind of a first pass at getting patch contacts, right? This soft finger model. And yeah, you can do it. I'd say more broadly, what I was trying to go at with that soft contact thing is what people call soft contact models are absolutely not like sort of first order versions of deformable stuff. And you still fundamentally have this sort of switch behavior of I'm touching it or I'm not. And you don't have action at it, force at a distance, right? So we're trying to get that behavior. And if you have deformation, my argument here is rather than have this smooth contact model that you maybe like tune some fudge factors in to get squishy stuff, the right thing to do is actually keep this, which is giving you this, I'm touching or not kind of flavor, and then model the deformation explicitly in some way. So this is a very dumb way of getting at like a very like first order, soft finger deformation, small patch contact kind of thing. There's lots of other ways to do it. I think for instance, the hydroelastic stuff in Drake is like a really good, principled approach to this that I like a lot. There's other ways to do it, but I think you should take a physics first approach to this and say, okay, there's deformation. How can I model deformation, right? All right, I think it's probably about that time.
One more thing to say, I guess. Tune in next week, same place, same bat channel. Jesse Grizzle from University of Michigan will be here, and check out the videos on YouTube and so on and so forth. Thank you again, Zach.
All right. Thanks, man. I mean, you're kind of the home crowd.